Everyone. Thank you for joining us tonight. I'm Cora Weeks and will be hosting this webinar on behalf of the NNA. I do hope you can hear me well. There is a chat box bottom left of your screen where you can write down comments or questions. Please, can you write there now to let me know if the sound is okay for you, if you can hear me? That would be very helpful. Thank you, Joe. That's great. Thank you. As we go, I will try to reply to any comments that you write there. And we'll take any questions that you have. Again, please do write them in the chat box and I will take them down and we'll give them to our speaker to answer after her presentation. Thank you, everyone. You can hear me. Excellent. So we are very happy to welcome Emma Beswick tonight, who will speak to us about genetics and methylation, their role in disease, and how we can achieve balance through personalized nutrition and lifestyle intervention. Emma is a naturopathic nutritional therapist who specializes in nutrigenomics. She is the founder and CEO of LifecodeGX, a company which provides professional genetic testing, training, and consultancy services. I'm really very much looking forward to this webinar. So please, on to you, Emma.
Thank you very much, Cora, and I hope everyone can hear me too. So yes, today I'm going to talk about methylation. I think it's a very topical subject, especially with news articles about folic acid and whether that's going to be introduced as a mandatory fortification of flour and foods and things like that. But it's also very, very relevant and ingrained in nutrigenomics and genetics. So I'm going to take the view or present a argument that you can have too much of a good thing with methylation, as well as obviously not enough. Okay, so that's a little bit about me. Cora has introduced me. Those are my contact details if anyone does want to get in touch with me after the webinar. So what we're going to talk about is, quite briefly, a little introduction to nutrigenomics, then go into methylation itself, what methylation is, particularly from the perspective of synthesizing methylation donors, such as SAMe, and then actually the application of methylation or methyl donors, such as SAMe, followed by just some information about practitioner support that we provide around methylation and genetic testing. So, to introduce genetics and nutrigenomics, first of all, a very, very high-level overview of genetics. So this is a representation of our genome. A genome is basically the code. All our genetic code is our genome, and it's organised on chromosomes, pairs of chromosomes, which can be compared to books in a library. And within those books are sentences or genes, which are constructed from codons, which themselves are made up of bases. So you may have heard of the letters A, G, C, and T. Those are the bases. And on a practical level, the genes code for proteins, and then it's the proteins that have the effect in the body. And some little stats there, if you're into numbers, about how many genes we have and how many bases we have. So genetic variation is about identifying variants in that genetic code. There are different scales of genetic variation. You can have a whole gene missing, a whole chromosome missing even, but mostly we look at SNPs. So a SNP is where there is a single nucleotide change. So it's a letter change. And if you do see here, we actually have a G, which we would describe as the wild type. So this is the code. You've got 3 T's, a C, G, and A, a T, and a G, and a G, and ATA. And a T, a G, and a G usually code for the amino acid tryptophan. If we have a variant which changes the G to an A, instead of coding for tryptophan, that code actually is a stop. It's like a full stop in a sentence. So it actually curtails the gene that is being coded for and makes a shorter gene or shorter protein than was designed to happen. So you can imagine in that case, if it's such a severe impact, it's likely to change the function of that gene fairly significantly as well. So not all SNPs have such a significant impact. Some of them don't actually have any impact at all. They don't change the amino acid and there is no known effect. So that's just an example. And then what we do when we get genetic code, so it's all well and good knowing what the letters are, but it's about interpreting it. For me, this is what genetic testing is all about. It's about, so what does it mean, and how do you represent that? So when we talk about an allele is another word for the letters. So you can have a situation where someone does a test and they reported a wild type. So this means there is no change. Usually the wild type is the ancestral type, and that usually is beneficial. Not always, but it's usually beneficial. In our reports, if something's beneficial, we code it as green. It doesn't just mean whether something has changed, the colour coding. The colour coding actually reflects the meaning or the effect. So here we've got a heterozygous genotype, which is one allele changed, and a homozygous genotype, which is where both the alleles are the variant, the alternative letter. And usually that means there is less gene activity, which is also usually negative in its effect. So that's a very, very quick overview of genotyping. And here is an example. So typically on a genetic report, you would see the gene name. So in this case, VKORC1 is actually a gene that codes for vitamin K recycling. So it's responsible for recycling vitamin K into its active form. This little section here with the RS number reflects the unique place on that gene that we are examining. So that's called a reference sequence ID. And that's the best way of knowing that you're talking about a specific thing. And then the result, in this case, I'm showing a homozygous result, which is the variant, which is negative because it means actually that change, that genetic change, makes that gene less effective at recycling vitamin K. Because we know that a large part of vitamin K status is dependent on its recycling, that can have quite a big effect. And what you might see in that case is people with this genotype are more predisposed to bruising or bleeding easily because of a lower vitamin K status. So what we would do as naturopathic nutritional therapists is we would find out the genotype, we would ask the person, are they experiencing any of these symptoms, in order to ascertain whether that seems to be really happening, and then advise them about how to keep up their vitamin K levels with a nutritious diet. So that's an example with a personalised interpretation there of the meaning of the variation. Okay, one of my big philosophies is that context is key. So it's not really that much use just looking at a genetic result. Sometimes it can be, but most of the genetics that we look at are variable according to a person's environment. So that's their diet or their lifestyle, other aspects of their lifestyle. And that is known as epigenetics. So people's genetic code is actually fixed. However, whether those genes express and to what extent the code or a variant would have an effect is very much dependent on the environment that those genes exist in. And you'll be familiar with the ATM acronym, the antecedent, trigger, and mediator. So in those terms, the antecedent is someone's genetics. A trigger is something in the environment that acts on the gene to make it behave in a certain way, whether that's positive or negative. And then the mediator is both. And the functional medicine tree that you might be familiar with here has genetic predisposition right at the heart of it, at its roots, really. And that tree has been part of the functional medicine movement for a long time. And indeed, genetics have been part of that whole philosophy and way of looking at health and medicine for quite a long time. Okay. So, again, one of the things that I feel is very important is that when people do genetic tests, they work with a trained health professional who knows how to use that information properly and competently. And I've mentioned environment, but these are other aspects that you would look at alongside genetic results. You would look at the family history, the individual's health history, their symptoms, and other functional test results. And as a nutritional therapist, you would be looking at all those things anyway, and the genetics is just another part of that picture. So it gives you a more complete picture. But I don't advocate just looking at genetics in isolation, because people can have the same genes and the same variants that exhibit very different responses or symptoms. Okay. So a little bit of terminology, nutrigenetics, nutrigenomics, the effects of genetic variation on dietary response. That's the nutrigenetics, and nutrigenomics is the role of nutrients in gene expression. And I'll show you some examples in a minute. So nutrigenetics, it doesn't really matter that much if you get these two terms confused, because they're all relevant in the context of genetic testing and nutrition. But nutrigenetics is more about if you have a gene coded in a certain way, then the effect of that gene variation will affect your dietary response. So, for example, lactase metabolism, which I'm going to show you as an example in a second. We've mentioned vitamin K. CYP102, which is in the middle here, affects your response to caffeine because it affects the speed at which you metabolize caffeine. So if you have a slow CYP102 gene, you're more likely to have caffeine in your system and being active for longer. So you're more likely to have a stronger response to it, or at least a longer response to it. Whereas if you have the fast version of the gene, the caffeine is removed more quickly. Some other examples are BDR, which is a really, really important one. So that's a vitamin D receptor gene, which affects someone's sensitivity to vitamin D. So what this means, in other words, is that two people could have the same level of vitamin D, but someone with a compromised or less sensitive BDR gene would not feel the benefit of the vitamin D so strongly as someone without those variants. So someone with variants, effectively will need to be at a higher level all the time. So their healthy or beneficial range would be higher than someone who had a wild genotype, no variants, and a more sensitive vitamin D receptor. So that affects their response to vitamin D. I'm not going to go through all of these. They're just examples for you to show the variety of genetics and environmental responses that are out there. Okay, so a little example, partly get you used to some of the symbols that we use as well. So on the left-hand side here, we're starting off with lactose. Maybe someone has drunk some milk or eaten a yogurt. The LCT gene is responsible for coding for the lactase enzyme, which breaks down lactose into galactose and glucose. Now, normally, when people have finished weaning or been breastfed, the LCT gene is switched off. This is the global ancestral genotype. So historically, we would not have had a need to continue to digest milk after weaning. So the gene switches off. However, there is a variant on that gene that means the gene continues to be expressed, and most Caucasians actually have that variant, which means they can continue to digest lactose as adults. But actually in Asia, or certain parts of Asia, only 2% of people have that gene variant. So that gene variation has evolved over thousands of years so that some people in certain parts of the world can digest milk and others can't. And that's probably just evolved as we've evolved our farming cultures. Okay, so that's just an example of what a gene does in transforming one substance to another. Okay, and this is basically what you might see in a report, which just is a repeat of what I had just told you. In this case, the wild is colour-coded red because that's actually got a negative impact, and the variance, whether that's a heterozygous or a homozygous, allows the gene to be active in adulthood. So that's coded as green because it seems to be beneficial. Okay, this is where it gets a little bit more interesting in nutrigenomic terms. So this is where nutrients actually impact gene expression. So it's slightly the other way around. And all the things here are relevant in methylation as well. So we've got here, for example, that folate or methylfolate is involved in the activation of B12, which I'm going to go into lots of detail about. That magnesium is also really, really important in helping a gene called MAT1A make a substance called SAMe, which is the master methyl donor, which we'll also go into more detail about. So all of these things are about nutrients, key nutrients, essential nutrients on the whole, that affect gene expression in a very, very significant way, and particularly in methylation. So I'm going to go into some detail now about methylation itself. So what is methylation? If you asked a person on the street or a client what methylation was, then their eyes would probably cloud over and they would look at you a bit oddly. So quite simply, methylation from a biochemical perspective is the transfer of a methyl group, so a carbon and 3 hydrogens between two substances. So the starting substance is demethylated and the end substance is being methylated. That's what methylation is. It's just this little chap here, the carbon and 3 hydrogens. What that actually means from a functional perspective is that it's needed for all these key things and many, many more. So it's actually involved in hundreds and thousands of reactions in the body. But obviously DNA synthesis and repair, neurotransmitter synthesis and metabolism, energy and also immunity, detoxification are all massively important functions within the body. And this methylation, methyl activity affects all of them very significantly. If methylation is imbalanced, then it can have a lot of very, very detrimental effects. And a lot of these effects are seen in chronic illness. They don't necessarily happen quickly, but they happen over time and they build up over time. So it's becoming more and more important with the incidence of chronic illness rather than acute illness, and also understanding your risk of chronic illness, because people tend not to think about it until things have progressed a certain way and they're actually symptomatic. But these are some of the things that poor methylation or imbalanced methylation can lead to. So methylation dysfunction is very common, unfortunately. What you will usually hear talked about, and it is more common, is undermethylation. So this is because of insufficient methyl donors or other nutrients that are needed to support it. It could be because of genetics or SNPs, insufficient substrates, so the starting substance, which again are nutrients, so that's diet related, or inhibitors like heavy metals or ammonia, for example, might disrupt methylation and lead to symptoms of undermethylation. One thing to be really aware of is that don't assume that someone is just undermethylating, and don't just throw methyl folate at that person, because some of the symptoms of undermethylation are the same as symptoms of overmethylation. So if you assume wrongly and you don't have sufficient information to make that judgment, then you can actually make things worse by putting more methyl nutrients into that system and over-methylating a person even more. So this is what I'm going to talk to you about today, partly how to tell the difference. But over-methylation is thought to be a problem in about 15 to 20% of people. So it's quite a significant number of the population. Okay. But whenever you see any methylation report, you will see variants because they are all very common. So even though people have genetic variants on these pathways, it doesn't necessarily mean that it's out of balance, because some of them might kind of balance each other out. Okay. So methyl donors. Everyone's probably heard of methyl folate or 5-MTHF. That's a major one. You might not have heard or think about betaine as being a methyl donor, but it is. Its long name is trimethylglycine, so the hint is in the name there. And then finally on here, SAMe, or the long name is S-denyl L-methionine. This is often known as the master methyl donor because it's the most important methyl donor in the system. So let's see how these things are actually used in methylation. So they all have a CH3 group. Okay, so this is a very, very high level overview of two of the most important cycles or subcycles in methylation. And they're really important because they make these methyl donors. So I'm going to go into detail for this, but just at a top level, we can see that starting with folates get converted into different forms of folate, ultimately ending up as 5-MTHF, which is methylated folate. And there's a really important gene here that you probably have heard of, which is MTHFR, and that gene converts folate into methylfolate. So if it isn't working very well, that, for a start, impacts the availability of methylfolate. Now, that methylfolate is actually then a cofactor for the methylation of B12. So it's needed, first of all, to methylate B12. So then B12 becomes methyl B12, which is its active form. And then that methyl B12 actually methylates homocysteine. And in that process, homocysteine is converted to methionine. So what's happening is a methyl group, a methyl donor, is being passed around. So it's synthesized in the first place as part of methylfolate. So it's the methyl in methylfolate. The methyl is then passed on to the B12. So it's the methyl in methyl B12. And then it actually methylates homocysteine. So methionine is a methylated form of homocysteine. And then the methionine is converted to SAMe with the help of magnesium. And SAMe is the master methyl donor, which then methylates lots and lots and lots of other things by passing on its CH3 methyl group. So that's basically what methylation is. This is the synthesis bit in high level, but it's already showing you that the methyl is effectively just being passed around to activate certain other reactions. I'm going to go into a bit of detail about this because it really does get more interesting and you can see which genes impact that. Okay, so the folate cycle itself, this is a drill-in. So on the previous diagram, we just had a very simple folate to methylfolate, but now we're drilling in and looking at it in a lot more detail. So the key functions of the folate cycle, first of all, are DNA synthesis and repair. So this is this little cluster here, which we hadn't looked at before, because up to now we've only looked at methylfolate synthesis. So methylfolate is here, right at the bottom, and we can take in folic acid or feed folate, go right to the bottom to make methylfolate, or because it is a cycle after all, the methylfolate can cycle round here, like methylene THF, or the folate can come straight down to make methylene THF, and then that 5,10 methylene THF is needed to help the body make its own DNA and repair DNA. So those are the two main functions of the folate cycle, are DNA synthesis and repair, and to create methylfolate to start the whole methylation process going. There are a lot of genes involved which we're going to go into, and a lot of different nutrients, but primarily folate or folic acid, but also look, B2, B3 and B6 are cofactors throughout this cycle, and that's quite often why we see B vitamins delivered in a complex, or in nature they are delivered together because they are all needed to complement each other. And that's one reason why I'd be very, very cautious about supplementing single B vitamins. There are good reasons for that on occasions, but mostly you need all of them together for this reason. So what this diagram is showing is, again, you've seen the little blue symbols previously. So the blue symbols are the substrates or the substances. The letters in uppercase capital are the genes, and the purples are the cofactors. And then the little yellow or green dots here are people's genetic results. So they represent whether the gene is fast or slow or changed or not. And then we also talk about functional testing as well with genetics. So you can look at the genes and see what someone's predisposition is, but then often it's useful to have your suspicions backed up by functional testing as well, or by looking at symptoms or all of them together. If the folate cycle goes wrong, then there are lots of consequences just within the folate cycle. So lots of things to do with fertility and pregnancy, and also cancer. So that's all to do with the DNA synthesis and the DNA stability. Also, anemia and fatigue are all to do with this, and I'll explain why in a minute. And then lots of things that are actually connected with insufficiency or excess of methylfolate, and that's where we're coming to, is too much methylation possibly a bad thing? That's the overview. So just to give you a little bit of insight into DNA synthesis and repair, when we start off and taking either folic acid or folate, it has to go through a series of transformations. Food folate is actually harder to absorb because it needs to go through more steps to absorb that through the intestine. There are more genes involved than folic acid, but then folic acid has its downsides too. So folic acid actually goes less efficiently through this pathway. So I'm actually going to not go into any more detail about folic acid specifically or food folate specifically at this point in time, but to move on to the active folate. So we get THF, which is tetrahydrofolate, which is made either from folic acid or food folate. And that tetrahydrofolate can be made into 5,10-methylene THF. And the primary pathway for this is this little side one here, which uses a gene called SHMT1. And SHMT1 needs B6 to work properly. So if it doesn't have B6, then it's not gonna be very efficient. And you can have all the folate in the world, but the B6 is going to be the thing that holds it back. So the tetrahydrate, all being well with the SHMT1 gene and B6 availability, the tetrahydrofolate is converted to this 5,10-methylene THF, and then the 5,10-methylene THF helps the DNA synthesis and repair. So if you don't have enough activity here, whether it's a problem with the folate in the first place, the folate supply, whether it's insufficient B6, or whether this 5-methylene THF is being stolen too quickly to make methylfolate, then if you have a problem with this and the DNA synthesis and repair isn't happening efficiently enough, these are some of the symptoms that you might see due to that underactivity. So anemia, like megaloblastic anemia, so where you have large red blood cells because the red blood cells can't form properly without the DNA synthesis working efficiently. And then you might have symptoms of fatigue and lethargy. Also immune compromised because the DNA synthesis is also key to white blood cell synthesis as well. And then also some risk of cancer initiation due to instability. So the DNA just not replicating and copying neatly and not being repaired. So there to be more breaks in DNA basically if this little subgroup of activity isn't nourished sufficiently. And then also finally fertility and pregnancy related issues. If it's overactive and there's too much of this, then that can be an enabler of too much DNA synthesis, and it can actually support cancer and too much cell growth. So there are medications that actually block this whole folate activity. So they block DHF here, and they block the activity here to stop that DNA synthesis happening. So drugs like methotrexate, which is a antifolate chemotherapy drug, would block folate for that reason. Okay. So moving on from the DNA synthesis little cluster to methylfolate synthesis, which is the other key objective of this cycle. So for methylfolate synthesis to happen, we need to convert the 510 methylene THF to 5-MTHF, which is methylfolate, and that uses or needs the MTHFR gene. And the MTHFR gene also needs other B vitamins as cofactors, so it needs vitamin B2 and vitamin B3. If there are variants on this gene, then they will likely slow down the activity. And the reason that you might have heard of MTHFR is because SNPs can reduce that activity quite significantly by more than 70% if both those two SNPs shown there are homozygous, which is a very, very significant effect. So if that part of the pathway is underactive, then it will reduce the amount of methylfolate available for methylation reactions further downstream. However, there is a small benefit in this, in that an underactive MTHFR can actually mean that there is more 510 methylene available to nourish the DNA synthesis and repair cluster. But it's all about getting the balance right. So whatever the situation is, people need folate. They need folate to be coming into the system and be doing what the body is designed to do and converting it either to the methylfolate or to supporting the DNA synthesis. The methylfolate can also be recycled back up into the folate cycle and to start that whole process all over again. But this little bit here needs B12. So we're going to come on to that next. Okay. You might have heard of folate trapping. Now, folate can be trapped right at the top of the process. And that can happen if there is a very, very, very high dose of folic acid, for example, the genes right at the top aren't able to cope with a certain amount. So that's a natural block on that. So you might have heard of methylfolate. That's more folate trapping or pooling rather than methylfolate trapping. So we're going to talk about methylfolate trapping here. So assuming that we've made it all the way to methylfolate and the folate cycle has done its job. So we've made methylfolate at the bottom here. Now, for that methylfolate to either go back into the folate cycle or donate its methyl group to B12, it needs B12. So B12 is the cofactor that allows the methylfolate to do anything, to be active. So it takes the methyl from the methylfolate and adds it to the B12, and the remaining folate, so the THF, goes back into the folate cycle. But if we don't have any B12 or enough B12, then that methylfolate is just going to sit there, or it's going to be excreted from the body. But that's why it's so important if you're thinking about looking at genetics and you just look at MTHFR, and many people do this, and a lot of consumers do this. They just look at MTHFR because that's the one they've heard of. They look at that and they see SNPs and they think that the person needs methylfolate. So they've given a methylfolate supplement, but that person may or may not have sufficient B12. So if they don't, then that methylfolate isn't going to do any good at all. And in fact, it can be negative because the body has a natural sensor. It's got a natural feedback mechanism, which basically tells it, I've got a lot of methylfolate here. Stop making more. Don't make any more, please. Folate cycle, can you just back off? Because I'm already drowning in methylfolate. So it actually pushes it back at this whole process. And can you see these arrows are multi-directional? So it's actually holding back that cycle, and therefore it's holding back the 5,10-methylene from being there to support the DNA synthesis. So that's why it's important to look at the whole picture and not just act on one gene result with one nutrient. So that's basically methylfolate trapping. So because it inhibits the DNA synthesis, some of the symptoms of that problem may well be anaemia and fatigue because of the lack of red blood cell support. So that's why with B12 insufficiency, you might get the same anemic symptoms as you would with folate deficiency. But unless you're doing some sort of testing or questioning about the person's diet and lifestyle, then you wouldn't know just going on that symptom whether it was a methylfolate or a folate deficiency or a B12 deficiency. Okay, so that's the folate cycle. And now I'm going to talk about the methionine cycle. So we're still talking about making methyl donors. We know about making methylfolate and we know about making methyl B12. But now, say we've made the methyl B12. So the methyl B12 methylates the homocysteine, makes the methionine, and then the methionine is converted into thymine. And in the process of donating its methyl group to methionine, B12 becomes unmethylated again, and it needs to be remethylated in this little mini cycle here, and it uses thymine and as its methylating donor. So you see there are lots of interreactions between all these methyl donors supporting each other, and there are different genes involved in each of these things. So that can be why when people start to be depleted in certain nutrients, everything just starts to slow and everything starts to grind to a little bit of a halt and becomes sluggish. And that's a very typical response in terms of methylation overall, typical response to either folate deficiency or insufficiency or any of the other Bs, because we've seen how they all work together, and particularly B12. Okay. And then what happens here is thymine. I'm not going to go into detail about DNA methylation, but one of the functions of thymine is to methylate DNA. And usually by methylating DNA, thymine is keeping certain genes within that DNA under control. So it's either suppressing them, because we don't need all our genes to be expressing in every single part of the body all the time. So mainly it's suppressing them, but you can have too much of it. So if DNA is hypermethylated, you can have a situation where tumor suppressor genes are suppressed and therefore can allow cancer to happen more easily. That's another link with cancer and methylation. It's a massive subject, all of its own. And what we're really talking about today is the kind of biochemical pathways of methylation rather than DNA methylation, which we can do another time. So that's just to give you that very small nugget of information about that particular aspect of SAMI and DNA methylation. So back to the biochemical pathway. Okay, why is methyl so important? So it's a cofactor. So we've already seen how it can be a cofactor for B12, for example. But it's actually a cofactor for any gene or any protein that ends in the letters MT, or in long word terms, methyltransferase. So all these gene names, they're all methyltransferases. And what that means is they need a methyl donor to work. They need a methyl donor as a cofactor. And you can see the very, very diverse functions that all these genes are involved in. So estrogen metabolism, neurotransmitter metabolism, histamine, melatonin and sleep, detoxification in general, so drug metabolism, and noradrenaline to adrenaline balance, which I'm going to show you some of these in action, and therefore the impact of having too little or too much methylation and what that might mean in a real scenario. But there are literally hundreds of these genes. You don't need to learn them all. You just need to know the rule about the MT. So yeah, anything that is a methyltransferase gene needs a methyl group as a cofactor. Okay, so histamine. Histamine, this is the pathway for histamine degradation. And I'm just going to show you one part of this. So there is a gene called HNMT, which converts histamine to N-methylhistamine. There's a surprise. It's methylating histamine. But in the process, that's part of the breakdown, the removal of histamine. So you see here we've got HNMT gene and we've got SAMI as a cofactor. So if we don't have enough SAMI, then that gene isn't going to be very efficient at removing or breaking down histamine. This pathway is more involved in histamine as a neurotransmitter in the brain and in the airways, whereas the one on the other side is more about gut histamine. However, there is some crossover. Often, because of this relationship between SAMI and histamine, high histamine is actually a sign of low methylation. So there is an inverse correlation between methylation and histamine. So if your client is experiencing histamine intolerance, then there are two possible scenarios that could be happening in relation to methylation. Firstly, their methylation process could be very subdued and insufficient, so they're hypomethylating and they're not making sufficient SAMI to manage the histamine removal. Secondly, or conversely, or all at the same time, the histamine could actually be depleting the SAMI. So in the process of trying to manage the histamine and remove it, the body is actually using up lots and lots of SAMI just to manage that whole situation, which means there's less SAMI left over elsewhere. But histamine methylation being inversely correlated is a very good thing to just have up the sleeve and to remember. Right. So moving on from histamine, catecholamines and COMT. So you see that COMT is an MT gene, and COMT is responsible for methylating catecholamines, and I'll show you some examples. Okay, so catecholamines include excitatory neurotransmitters, including dopamine, adrenaline, and noradrenaline. So we need COMT to break those down, and we need a methyl donor to support it. And that methyl donor could be, and usually is, SAMe. There are also hormones that are broken down by COMT. Estrogen in particular is broken down by COMT. And also things that we naturally think of as being very good, like the flavonoids in tea, are also degraded by COMT. Now, all these things can compete with each other as well. So if you've got a lot of estrogen, that can mean that there is less COMT and less SAMe left over to degrade the neurotransmitters. So that's one consideration. Another consideration is that if you have a lot of methyl groups, it might cause the COMT to work faster, and it might remove some of these things more quickly than you want them to. That's a less common scenario, but it does happen. Okay, let's just drill into estrogen as an example. So with estrogen, we have these hydroxy estrogens in the body, 2-hydroxy and 4-hydroxy, and they're the active estrogens. 4-hydroxy generally seem to be effective and good. 4-hydroxy isn't. 4-hydroxy is generally seen to be quite a dangerous type of estrogen because it can actually cause a lot of damage in the body. So we want these things to be removed efficiently, even the good stuff. Once it's done its job, we want COMT to be able to remove them and break them down efficiently. So you can see here that the COMT gene, with the help of SAMe, methylates both those estrogen types and makes them into the methyl version. So again, a lot of the time you don't need to learn these. You can tell by looking at the name of the substrate what it consists of, and particularly whether it's methylated or not. And the same with the COMT gene name. So you can see that it's a methyltransferase, hence the MT, but it's also a catechol methyltransferase. So that's what it's working on. That's the sorts of substance that it's breaking down. Okay. And as we've seen earlier, when we looked at the whole SAMe synthesis process, that genetic variants on all these other genes can affect the levels of SAMe availability, and therefore they can affect the speed at which the COMT gene works. That's COMT and estrogen deactivation. Okay, neurotransmitters. So this is a little bit extra information here. So this is the dopamine and noradrenaline and adrenaline pathway. So we start off with tyrosine, and tyrosine is converted to dopamine. And actually, it needs methylfolate. Indirectly, it needs methylfolate to do that. So the more methylfolate there is around, the faster that activity works. So someone who has a lot of methylfolate in the system, whether that's through natural folate cycle activity or whether they've taken supplements, can generate a lot more dopamine. So they're likely to be making more of it in the first place. The dopamine can either be degraded directly, so coming out here to the left, by COMT using SAMe, and also another gene called MAOB is involved in dopamine breakdown as well. And that's converted to a substance called HVA, which if you're doing functional testing, that's the metabolite that can be measured to see or give you an indication of dopamine levels. Alternatively, the dopamine can be converted to noradrenaline, which we want to happen. Noradrenaline is a good thing in moderation, and it's good for focus and things like that. But, and this is just a bit of a side thing really, if you have a lot of copper, copper can make that pathway work too quickly, and it can actually deplete dopamine, and people can feel quite depressed if they have low dopamine. Depressed because they're low dopamine, but actually quite anxious and jittery, and maybe even experience things like increased heart rate, palpitation, sweating, because they're creating more noradrenaline and adrenaline. And you see here, in particular, we have a gene called PEMT, which is responsible for converting noradrenaline to adrenaline. And so we know it's an MT gene, and it means SAMe. So that helps the person create more adrenaline. Now, that's not always a good thing. So adrenaline is our emergency hormone. It's fine when it's just triggered occasionally in a genuine emergency. But in today's world, we know that that happens more frequently than it used to. So one of the considerations for this pathway in particular, methylation, is methylation can really, really stimulate dopamine, noradrenaline, and adrenaline. It can push those levels up through the methyl folate link. However, we can also see that SAMe is involved in methylating those substances and breaking them down. So logically, you might think that methylation just works equally on the synthesis and on the metabolism. But unfortunately, that isn't always true, because you can have a slow COMT gene. So if you have variants on a COMT gene, then that's slowing that COMT gene down. Even if it's got a reasonable amount of SAMe in it, it will still be a relatively slow COMT gene. So you need to be a little bit careful about stimulating the neurotransmitters, especially with supplements, if you have a slow COMT gene, because the stimulation can outpace the ability to break it down, and it can push people into an uncomfortable feeling when it comes to those excitatory, stimulatory neurotransmitters. Another consideration is that we mentioned that COMT methylates estrogen and breaks estrogen down. So if there is a lot of estrogen around, a lot of the COMT enzyme is actually used up methylating the estrogen. So basically, if there's a lot of estrogen, the COMT that is available for neurotransmitter metabolism will be reduced. That's another reason why someone's ability to remove these neurotransmitters may be compromised if they've got high estrogen as well. So hence another reason to take care with methylation. So this is where methylation can be too much of a good thing, another play, because you can be pushing the synthesis part of the equation too quickly for the metabolism part of the equation to cope with. So that's summarised here. And the other thing is, in today's world, there are lots and lots of other things pushing these pathways, these excitatory pathways. So whether that's sugar, caffeine, or stress, they're all acting on these pathways. So you just need to be aware of that. And if someone is showing signs of hypermethylation, then that's another reason why to cut down on caffeine and sugar and to try and manage stress. Anxiety is one of the things that is a symptom of too much or too little. So if someone's got too much dopamine and excitatory things going on, then they can feel really jittery and anxious. Alternatively, if they've not got enough, there's a similar pathways work on making serotonin. So serotonin also needs methylfolate. If you've not got enough going on, so you've not got sufficient methyl donors, then you can feel anxious because you've got too little neurotransmitter synthesis happening. So again, if you're just looking at symptoms and you're not tuned into the detail and the nuances, you can actually make a very easily incorrect judgment. And indeed, that's what often can happen in GP practices or psychiatric practices. They can just look at the symptom but not look at what the underlying biochemistry is, and hence prescribe something that actually makes the situation worse and maybe pushes neurotransmitters even higher, and that's the problem in the first place. So we're nearly finished, but this is a summary of the catecholamines and estrogen and COMT. So this is dopamine. We want dopamine to be at this nice sweet spot where we feel happy and rewarded and motivated. The more estrogen someone has, the more the dopamine is pushed to the right, so it's pushing the dopamine up. Obesity is also pushing this up. Partly it's connected to estrogen, and stress is pushing dopamine up. So all these things are pushing dopamine over to the right-hand side. If you have a lot of methyl donors, that's making more dopamine. And if you've got a slow COMT gene, then that's helping to raise the estrogen, but it's also not breaking the dopamine down. So it's pushing everything over to the right. Conversely, if you don't have enough methyl donors, then you've got a risk of lower dopamine because you're not making enough in the first place. So that gets pushed over to the left, and you are more likely to feel low and can't be bothered and demotivated and all those things. But there are quite a lot of factors involved in this, as you can see. So there's the nutrients, there's the genes, there's the methylation, there's the detoxification, the hormones, and it's about being able to put it all together. Okay. So here, just to summarise, are some of the symptoms of methylation imbalances. So typically hypomethylation, not enough neurotransmitter synthesis, anxiety, cardiovascular disease because you're not converting the homocysteine to methionine, fertility issues because we're not able to replicate DNA tidily and safely for detoxification, and so on and so on. Hypermethylation, anxiety because too much going on in the brain, too much excitement, too much stimulation. Insomnia, similar reasons, inability to focus, hyperactivity, etc., etc. So you can see there are some similar symptoms and some different symptoms, but it's important to get under the hood and understand the why. So that's really some aspects of methylation. I've whizzed through it. If we take into account the intro about the genetics and SNPs and things, I've whizzed through methylation in about 45 minutes, which is just scratching the surface. We do a whole day seminar on methylation, so if you're interested, do look out for that. We also do lots of other reports as well. So here are some of the reports that we test, some of the subjects that we test for. Obviously, as well as methylation, we've got detoxification, estrogen balance, nervous system, are all slightly overlapping with methylation as well. So we do report some of the methylation genes in those other reports. But if you want to look at methylation in depth, you really need the methylation report, which actually includes about 50 SNPs. It's about 35 genes and about 50 SNPs. all of which are really, really important to consider. It's such a core thing just to look at MTHFR, and it actually, I find it quite upsetting when I see people making judgments off the back of that. Okay, this is the kind of just some key points about how we do things. So security is very, very important, and that's something that you should consider with whichever DNA testing company that you're using. Accuracy and quality, and then really interpretation. So how competent is that company, and how complete is that company at providing good interpretation for you? So I've used diagrams and pathways in this presentation, and that's the way that we do it in the report, so that you can see very visually where blockages might be, what nutrients and cofactors are needed to support it. And then the other thing we do is we run practitioner seminars, and we provide one-to-one support. So when you get genetic results, we provide a nutritional therapist to go through results with you over the phone as part of that purchase. And here's some of our seminars, and how you can find out more about them, basically from our website. The NNA approve all of our seminars for CPD, so you can count them towards that. And we've got our 2019 seminars soon to be announced. If you want to be kept informed about that, you can sign up to our newsletter, which you can do so on the first page of our website. And that's also how you register with us if you're interested. It's free to do that, and those are some of the benefits that you get as a registered practitioner. So that's the end of my presentation, and I'd be happy to answer any questions or some of the questions that have come up during the last hour. So I don't know, Cora, do you want to coordinate any questions?
Yes, thank you very much, Emma. That was a really clear and comprehensive explanation, and we had a lot of technical detail, so I'll definitely have to review and the webinar. It's a lot to take in, and I had quite a few ideas came to me for my clients while listening to you. So thank you very much.
You're very welcome.
Thank you. We did have a few questions. So a question from Yolanda. We had, do greens or other foods contain methylfolate?
Greens or SNPs?
Greens, green vegetables and other foods.
So folate in food needs to be activated. So when we looked at that folate diagram, the food folate all need to be activated and converted, but it's generally quite efficient. So once the food folate is absorbed, the first thing to consider is, what is the gut health like? Is the person likely to be able to absorb the folate easily? And also, even if they have good gut health, do they have genes that might impact that? So getting it in, but then the food actually does all need to be converted to methylfolate. The good thing is, if it's in natural food state, is often the same foods that include folate include all the cofactors. So they include other B vitamins to help that happen. So nature is providing us with that whole food in a way to smooth that process. Whereas if you just take folic acid, for example, that's not got all those other vitamins to help that activation process work.
Thank you. We had another question also from Yolanda. I think it's very much related to what you just said, but I will read it anyway. I'm a bit puzzled when Emma said that folate from food is more difficult to use than folic acid. I'm not sure that you said that, but there was something there. Did I hear it correctly? From what I know, folic acid is artificial and a no-no for people who have methylation variants. They need more active folate from greens. So I think you've already touched on this. Do you want to say anything more?
I can just summarise on it. In fact, let me just find that. Let me just find the top of this diagram. So basically, there are pros and cons to each. Folate is more difficult to absorb in the first place because it goes through these places here. So it's particularly the FOLH1 gene. So food folate needs to go through that breakdown. It's broken down from polyglutamate to monoglutamalic acid, or whatever the long name for folate is, whereas folic acid is already in that mono form, so it doesn't need to go through that process. I would say that's possibly the only benefit of folic acid relative to food folate. And then the benefits of food folate are what I said, that it is a whole food. It's got all those other good essential nutrients in it. And also, you're less likely to overdose with food folate, whereas it is possible to take a large amount of folic acid, which then basically starts to pool up here and use up all this DHFR enzyme, and you see this DHFR enzyme is used for the folic acid here, and also to convert the next step, whether it's food folate or folic acid. So if you have a lot of folic acid, that can actually crowd out the good food state folate that you would hopefully be taking in anyway. So yeah. So always, my view, personal view, is food folate first. Folic acid can be something that if people have got very, very compromised absorption, it can be something temporarily that can help with that, but then you've still got to make sure they've got all the other B vitamins.
And I suppose folate in supplemental form is even less likely to be helpful. If it's
so folate, again, yes, absolutely. If you take folate in supplemental form and it's just folate, it's got the same problem. You haven't got the other nutrients to support it. So you can get supplements that aren't methylated, and you can get supplements like folinic acid, for example, which kind of come into the whole cycle somewhere in the middle, but they still need other B vitamins to be activated and converted to methylfolate. So the other option is you can take methylfolate, but then you need to be aware of nourishing the DNA activity. So the methylfolate can go back around the system, but it then still needs the other Bs. Or for the methylfolate to be used, it has to have that B12. So again, if you're thinking about supplementation and you're thinking about methylfolate, please, please, please think about at least B12 and ideally all those other B vitamins as well.
Right, thank you. And also from Yolanda and Paloma, they wanted to know how common is hypomethylation. I think, if I heard correctly, you said that overmethylation is about 15%.
Yeah.
And do you know how common is hypomethylation in your experience?
It's very common. It's very common in terms of, so if you think about hypo as just not, firstly, not making enough famine or in the first place, very common. If you think about all the nutrients that are needed for that, then you could understand why a lot of people have got compromised methylation. So if they're not getting enough of any of the B vitamins, basically, and also magnesium and zinc are really, really, really important for the methionine cycle. And on top of that, protein. So you need the methionine, some methionine created from homocysteines, but you also need methionine protein intake to support that. And there's another pathway in the methionine cycle that I didn't go into much in any detail on, but that's this one here up through the middle, which needs betaine, which is made from choline. So then that's things like eggs as well. So because people's nutrient status is often suboptimal these days, that has such a direct effect on methylation, and a big part of the population are hypomethylating in some way.
You mean it is more epigenetic than genetically induced hypomethylation?
Yes, I would say so, although MTHFR SNPs are very common. So MTHFR is a key part of methylation, and SNPs, I think Caucasians, there is about a 50% of Caucasians have at least one MTHFR SNP. So that will be impacted in some way. And then the other thing is that lots of things deplete methyl donors as well, including stress. So if you're making a lot of adrenaline, for example, constantly, you need SAMe to metabolize that adrenaline, and so you're draining the SAMe and you're using it up. Or if you've got a lot of histamine and inflammation, that's using it up. So that it's happening from both directions.
So hypomethylation is much more common than hyper.
Yeah, hypo is much more common than hyper. Yes.
Yeah. Thank you. Another question is, I'm not sure if I understand it correctly. When do you use TMG and when SAMe? I suppose in terms of supplements. I'm not sure, Yolanta, what you mean.
Yeah, so trimethylglycine. Yeah, so you do have lots of different options when you're looking at supporting methylation. So trimethylglycine is effectively betaine, so that helps homocysteine to be methylated to methionine. I personally feel slightly wary about supplementing with direct end products. So SAMe isn't actually something that nutritional therapists are supposed to use in the UK. You can get hold of it, but because it can have quite a significant effect, and if, again, you're not careful with dosage, it's quite easy to overdo it and to overstimulate. So yeah, you can experiment on yourself as a therapist and see what you think of it. I think trimethylglycine is very good because it's providing a methyl, but it's also providing glycine, and that can help with glutathione synthesis and lots of things as well. And it tends to be a more subtle methylation support mechanism because it still has to go through methionine to generate the methyl donor for SAMe.
Thank you. And Judy is asking, do we need to have trained with you before using your tests?
The short answer to that is no. We like you to have trained with us because it is complicated. So particularly methylation is complicated. I think some of the other tests aren't quite as difficult. If you train with us, you obviously get that depth and you feel competent or more competent at the end of a day. We do case study work well. However, if you can't make our training, we we're still happy for you to use our test because we provide the one-to-one support as well. So if you haven't done our training, we will still provide you that one-to-one telephone support to go through results with you, whether it's for you or for your client. But it's helpful to give you a good start if you do the training.
Right, thank you. It's good to know. Deidre asks, what are your thoughts on government proposal to add folic acid to flour?
Yeah, it's a difficult one, really, isn't it? Very political. I mean, my view is food first, as in natural, folate first. And I think when we discuss the pros and cons, just the cons of folic acid are that it doesn't include all those other things, so it's just part of the equation. So it's giving our system part of what it needs, but not the whole thing. So there is a risk that it actually disrupts certain parts of the sequence, I think, and it's no way as good an approach as going a more natural route. I do appreciate the reasons, why they're saying they want to prevent birth defects, and that's had a positive impact in certain countries. But I think there are other ways of doing it. Like maybe they should consider just free supplementation of food state nutrients or something like that, or educating people better.
Yeah, definitely. Yeah.
And that's our job as nutritional therapists.
Yes,
So
encourage people to have more greens.
exactly.
Excellent. Thank you very much, Emma. I think these were all the questions. I hope I haven't missed anything. I'm just quickly through to double check. But I hope I haven't missed anything.
Okay. Well, if anyone does have any questions, then please do feel free to contact us. We're happy to help with any enquiries at all. Even, is genetic testing something that is relevant for a particular client? It isn't always, but please do feel free to get in touch and register with us as practitioners as well. And our details are there.
Wonderful. Thank you very much, Emma. And thank you, everyone, for joining us tonight. As usual, the recording will be available within a week, and you will receive an email with a link to the recording and a link to download the slides of the presentation. So have a very good evening, everyone, and hope to see you soon again. Bye-bye.
Bye.